Let's consider the following scenario. We are tracking the mass of bacteria in micrograms in an experiment in terms of the number of hours t since noon. So this graph relates the mass of the bacteria to the number of hours since noon. So I can vary the initial number of hours since noon, so the initial value of t. And as I vary the initial value of t, I have a change in t of 1 unit. I have the initial mass of the bacteria represented by this first blue segment. The second blue segment here represents the mass of the bacteria 1 hour later. And then I have a green vector representing the change in the mass of bacteria. So as I vary this initial value of t, all of those values vary. But it looks like this final mass of bacteria is proportional to the initial mass of bacteria, where that final mass is some number of times as large as the initial mass of bacteria, and it doesn't matter what value of t we pick. So if we compare this final output to the initial output, so right now 16.12 divided by 13.9, we get a value of 1.16, which means that the mass of the bacteria at the end of this 1 hour interval is 1.16 times as large as the mass of the bacteria at the beginning of that 1 hour interval. As I vary the initial value of t, those values vary, but the ratio of the final mass to the initial mass is constantly 1.16. And therefore, over any 1 hour interval, the final mass of bacteria is 1.16 times as large as the mass of the bacteria at the beginning of that interval. And therefore, we say the 1 hour growth factor for this relationship is 1.16. Since the mass of bacteria at the end of this 1 hour interval is 1.16 times as large as the mass at the beginning of the interval, we can say that the mass of bacteria at the end of the interval is 116% of the mass at the beginning of the interval. So let's write that out. So the mass at the end of the interval is 116% of the mass at the beginning of the interval. And that's because when we're doing this percent comparison, we're saying the same thing as we said before, but instead of measuring the final mass in terms of the initial mass, we're measuring it in terms of 1/100th of the initial mass of bacteria. So our measurement becomes 100 times as large. Now, let's compare this change in mass of bacteria to the initial mass of bacteria. So right now, the change in mass of bacteria is 2.31 divided by 14.42 times as large as that initial mass. So let's show that. So 2.31 divided by that initial mass of 14.42 is equal to 0.16. So the change in mass is 0.16 times as large as the initial mass. And as we vary the initial value of t, that change in mass is constantly 0.16 times as large as the mass of bacteria at the beginning of the 1 hour interval. This measurement of 0.16 tells us the size of the change in mass to the initial mass. So if we think of this in terms of percentages, we can say that the change in mass is 16% of the initial mass over any 1 hour interval. And therefore, we would say that we have a 1 hour percent change of 16%. And again, let's write that out. The 0.16 can be thought of as 16%, where the change in mass is 16% of the initial mass. And therefore, we have a 1 hour percent change of 16%. It is common to report percent changes, and we can relate percent changes back to ideas of times as large as well as growth factors.